This video is brought to you by mywayteaching.com.
In this part, let us study about radiation. Conduction and convection, they require some material as a transport, isn't it? Whereas these modes of heat transfer cannot operate between the bodies which are separated by a distance in vacuum. But the earth does receive heat from the sun across a huge distance, and we quickly feel that warmth of the fire nearby, even though that air conducts very poorly, isn't it? And before convection can set in. What is the reason for all those things? The third mechanism for heat transfer needs no medium. So that is called as radiation, and energy so radiated by electromagnetic waves is called as radiant energy. Okay, the energy which is radiated by the electromagnetic waves, we call that one as radiant energy. Is that fine? In an electromagnetic wave, electric and magnetic fields oscillate in space and time. Like any wave, these electromagnetic waves can have a different wavelengths, and even they can travel in vacuum with the same speed, that is the speed of light, which we all know, that is 3 into 10 raised to 8 meter per second, isn't it? Here, heat is transferred to the earth from the sun through empty space. All the bodies emit radiant energy, whether they are solid, liquid, or gases. So, the electromagnetic radiation emitted by the body by virtue of its temperature, like radiation by a red hot iron or light from a filament lamp, is called as thermal radiation. So, this thermal radiation is due to the it is by the virtue of the temperature of the body. When this thermal radiation falls on other bodies, it is partly reflected and partly absorbed. So the amount of heat that a body can absorb by radiation, it depends on the color of the body. We all know that even black bodies, they absorb much, right? And even they emit radiant energy better than the bodies of lighter colors. So this fact, it finds many applications in our day-to-day life. For example, we wear white or light colored clothes in summer, so they absorb the least heat from the sun. However, during winter, you see we use dark colored clothes which absorb heat from the sun and keep our body warm. Even the bottoms of the utensils for cooked food are blackened so that they absorb maximum heat from the fire and give it to the vegetables to be cooked. And even you can take some other examples like thermos bottle is a device to minimize heat transfer between the contents of the bottle and outside. It consists of a double walled glass vessel with the inner and outer walls which are coated with silver, so that radiation from the inner wall is reflected back to the contents of the bottle, and the outer wall similarly reflects back any incoming radiation. So the space between the walls is evacuated to reduce that conduction and convection losses, and the flask is supported on an insulator like cork. So it is useful for preventing hot contents from getting cold, or alternatively to store cold contents, for example like ice. Okay, so here all we use this application of radiation, means the thermal radiation. The black colors will absorb much and the light colors will not absorb that much compared to the dark colors. Now let us study Newton's law of cooling. Okay, see, we all know that hot water or milk, when left on a table, it begins to cool. So ultimately it attains the temperature of that surroundings. See, to study how a given body can cool on exchanging heat with its surroundings, you just let us perform a very simple activity here. Okay, you just take some water, say 300 ml, in a calorimeter with a stirrer and cover it with a two-hole lid. Fix the thermometer through a hole in the lid and make sure that the bulb of the thermometer is immersed in the water. Note the reading of the thermometer. This reading you take it as T1 is the temperature of the surroundings and heat the water which is kept in the calorimeter till it attains a temperature say 40 degrees Celsius above room temperature. Then stop heating the water by removing the heat source. Start the stopwatch and note the reading of the thermometer after fixed interval of time. Say after every 1 minute of stirring gently with the stirrer, continue to note the temperature T2 of water till it attains the temperature about 5 degrees Celsius above that of the surroundings. Then you plot the graph by taking each value of temperature, that is delta T is equal to T2 minus T1 along y axis and the corresponding value of T along x axis, as you can see in this particular figure. And from this graph you will infer how the cooling of hot water depends on the difference of its temperature from that of the surroundings, isn't it? And you will also notice that initially the rate of cooling is higher and it decreases as the temperature of the body falls. Here initially it is higher but it decreases as the temperature of the body also falls. And this shows that the hot body loses heat to its surroundings in the form of heat radiation. And the rate of loss of heat, it depends on the difference in temperature between the body and surroundings. So Newton was the first to study in a systematic manner the relation between the heat lost by a body in a given enclosure and even its temperature. Okay, so according to Newton's law of cooling, the rate of loss of heat, that is minus dq by dt, okay, is directly proportional to the difference in temperature, that is delta T is equal to T2 minus T1 of the body and the surroundings. And even this law holds good only for small difference of temperature. And also the loss of heat by radiation, it depends upon the nature of the surface of the body and even it depends on the area of the exposed surface. So we can write this law in a mathematical form, that is dq by dt is equal to k into T2 minus T1, where k is a positive constant depending upon the area and nature of the surface of the body. Suppose a body of mass m and specific heat capacity say S is a temperature T2. Let T1 be the temperature of the surroundings. If the temperature falls by a small amount say dT2 in time dt, then the amount of heat lost, we can write it as dq is equal to m, that is mass of the substance and specific heat is S2 D2. Rate of loss of heat is given by dq by dt ms dt2 by dt. And from these equations, that is from the equation first and equation 3, we can write minus ms here minus will come, isn't it? dt2 by dt is equal to k t2 minus t1. So we can write dt2 by this capital K is equal to K by ms. Okay. So on integrating, we get log to the base e t2 minus t1 is equal to minus kt plus c, or in other words t2 is equal to t1 plus c into e raised to minus kt, where c is equal to e raised to c. So it enables us to calculate the time of cooling of a body through a particular range of temperature. For small temperature differences, the rate of cooling due to conduction, convection, and radiation combined is proportional to the difference in temperature, and it is valid approximation in the transfer of heat from a radiation. Okay, it is a valid approximation in the transfer of heat from a radiator to a room, the loss of heat through the wall of a room, or the cooling of a cup of tea on the table. So, this Newton's law of cooling can be verified with the help of the experimental setup that you can see here. See, this setup consists of a double-walled vessel V containing water in between the two walls. A copper calorimeter C containing hot water is placed inside the double-walled vessel, and two thermometers through the corks are used to note the temperatures T2 of water and calorimeter and T1 of hot water in between the double walls. Okay, this is calorimeter and this one is the vessel. The temperature of hot water in the calorimeter is noted after equal intervals of time, and the graph is plotted between log E T2 minus T1 versus time, as you can see in this figure B, and the nature of the graph is observed to be a straight line having a negative slope, as you can see in this particular graph, isn't it? So now let us solve a very simple problem. A pan filled with hot food cools from 94 degrees Celsius to 86 degrees Celsius in 2 minutes when the room temperature is at 20 degrees Celsius. How long will it take to cool from 71 degrees Celsius to 69 degrees Celsius? So this is the question. See, the average temperature of 94 degrees Celsius and 86 degrees Celsius is 90 degree. Which is 70 degrees Celsius above the room temperature. So under these conditions, the pan cools 8 degrees Celsius in 2 minutes. So we can write using the equation that we studied before. Change in temperature by time is equal to K into delta T. Okay, so that change in temperature is 8 degrees Celsius. The time is 2 minutes. K into 70 degree Celsius. So this is the first equation. And coming to the second part, the average of 69 degrees Celsius and 71 degrees Celsius is 70 degrees Celsius, which is 50 degrees Celsius above the room temperature. So K is same for this situation as for the original. So that is 2 degrees Celsius. We don't know the time. So when we divide these above two equations, we get 8 degrees Celsius by 2 minutes is equal to K into 70 degrees Celsius. 2 degrees Celsius by time is equal to K into 50 degrees Celsius. So we get time, that is 0.7 minutes, which is nothing but 42 seconds. Okay.